Welcome to another Refrigeration Mentor podcast and the CO2 Monday show. Super excited again. I always love this time of my week because I get to hang out with experts from around the world and I get to learn more about CO2. Always diving into the latest technology, always diving in on different technical topics. And this week I wanted to have my good friend Nabil Cook come and hang out with me and teach us how to properly size and select different compressors. We know I've done many talks with Bitzer and Copeland and Dorin and all these compressor manufacturers, but it's really good for you to understand how to size them and select them, because I know for sure this is going to help you out. Even knowing where the software is half the time is half the battle. It will help you out. But we're going to be diving in today, learning how to size and select different compressors for a transcritical booster rack. So if you're listening on the podcast and you want to watch this episode, I'm going to be putting in the description the link to show you the step-by-step. But listen to what Nabil is saying while we're going through this and the things that you need, because you need some information. You can't just size a rack without certain information. So we're going to be diving into specific applications, and we've drawn out a little plan on kind of a rack that you potentially could size in the future. Super excited for the show. Nabil, welcome to CO2 Mondays. How you doing, Nabil?
Thanks, Trevor. It's a pleasure to be here. Hello, everyone. I hope we're all well.
Yeah, awesome. So Nabil is an expert at sizing systems, CO2 systems, designing them from ground up, from nothing to this amazing product, from doing heat recovery on it, from transcritical, subcritical, everything in between, heat pumps and so on. So his credentials are a list long. It's huge. But we're going to be diving into three specific compressor manufacturers today, the ones that we see all around the world globally: Bitzer, Dorin, and Copeland. There are many other ones out there, Bach, Frascol. There's many other ones. Panasonic, LG, Toshiba. The list goes on and on for CO2 compressors, Vilter. But we're going to focus on those three today, and probably down the road we'll do some other ones. But we're going to dive into it. And me and Nabil decided that we're going to do, on the transcritical side, Nabil, right, 100 kilowatts, 340,000 BTUs. I think that's what we'll do for the medium temp.
That's right, 100 kilowatts. Pardon my ignorance of any units that aren't used in Britain. I do apologise up front.
That's what you got me here for. Not only a pretty face on here, Nabil, but here to help convert. And then on the low temp side, on that rack side, we're going to go with 25 kilowatts. So that's probably close to 85,000, 90,000 BTUs on the low side. Conditions we're going to use today, we're going to use plus 20 Fahrenheit, minus 7 Celsius, because this is the information you need, as well as on the low temp, we're going to do minus 20 Fahrenheit, which is around minus 29 Celsius. And the ambient, I think we said we're going to use 95, which is about 35 Celsius. Nabil?
That's absolutely right, which is kind of familiar for a lot of users in Europe and also in the Americas, to be fair.
Yeah, because that's the main things you need when you're going to design a booster rack, right? That's some of the main things, right?
Well, that's it. Compressor sizing is all based on compression ratio and displacement. So the most fundamental thing you need is an understanding of those SSTs and also that high side condition.
Yeah, awesome. So let's dive into some terms before we dive right into to start selecting it, because there's capacity control, there's going to be efficient motors versus other motors. You want to dive into some of those terminologies that will that really help out the people that are listening?
Absolutely. Capacity control is a way of reducing the compressor's displacement, its output, to more closely match the load that's being experienced at any given instance. Now, there are multiple ways of doing that. Some are rougher than others. For instance, you have something called a slider on some compressors, which is basically the equivalent of a clutch on a car engine. All it basically does is disconnect the rotation of the compressor from the main shaft, so that you are disconnecting the compressor output from the load. That's one example, a very rough example of capacity control. Another is blocked suction, where for one of the cylinders, say on a semi-hermetic reciprocating compressor, you block it off so that it can't actually contribute to the compressor's overall output. But then we get to, let's say, more advanced or closer versions of capacity control. One of them is an inverter, otherwise known as a variable speed drive or a variable frequency drive, where the speed of the compressor is modulated, and this is proportional modulation, so there's no limit on that, on basically how close a frequency you want to achieve. Now that's a lot more efficient because you're not wasting power in delivering that part output, whereas with stuff like sliders or blocked suction, you sadly are wasting an amount of electrical consumption in those methods of capacity control. There is one more method, and it's called digital or pulse width modulation capacity control, and that's using a pulsing method on the head of a compressor. So basically, these can be used on scroll compressors and on reciprocating compressors, where the head of the compressor is using pulse width. Solenoids is basically modulated in and out within a cycle time, such as 6 seconds, 3 seconds, whatever that might be. This is sort of in between. It's less wasteful of the electrical side than block suction methods and slider methods, but it's not quite as energy efficient a version of capacity control as variable frequency drives or inverters.
Yeah. And that all depends as well too, because depending on the compressor will depend on the range. So maybe one that has that modulation, that type of digital or cap, because Bitzer called it CR2, Copeland calls it digital, Frasgol calls it Capiflex. There's lots of different names for them depending on the models, but depending on the motor themselves will depend on the range. So some can ramp down a lot lower than others. If it's a permanent brushless permanent magnet motor, those ones are going to have a bigger range than that just a standard across the line motor. So this is something you need to go in and really understand before you design that rack. Which ones are you going to put on the rack itself? Correct?
That's a great point, Trevor. Is block suction depends on the number of cylinders or heads that are available. So that it means that you can either have 50-50 or third, basically, on reciprocating compressors. With variable frequency drives or inverters, your sort of control range is dependent on what your maximum frequency is. Because the minimum frequency sort of is invariably 25 hertz to 30 hertz. Because at any speed lower than that, you just can't keep the mass of metal moving. So what then limits whether it's 50% you can get down to, or 40% or 30%, is whether your maximum frequency is 60, 70, 80, 100, or even with some compressor models, 120 hertz.
I've seen up to 254. So massive on magnetic motor. So 60 was the limit. That's where it was starting. I'm like, what? 60? That's the low end. The top end's 250. I did a video on my YouTube channel. You guys can go check it out. But you got to understand the components in your system. So, well, I think, is there any more terms that we should talk about with everyone?
There are a couple. There is gas cooler outlet. So this is basically the temperature that your gas cooler coil or your heat rejection device cools the CO2 outlet down to above the ambient temperature. And we'll look into that in a minute. Yep. Other terms that we might need to look at are superheat. So superheat is basically the amount of sensible heating that you put into the refrigerant vapor past saturation to ensure that there are no sort of micro entities or droplets of liquid remaining in that refrigerant vapor, to therefore protect the compressor.
Yeah, and that's very important because with CO2 compressors, it's different superheats. That oil carries over or saturates with CO2 way easier, even when there is superheat. So this is something about the characteristics, and we talk about this time and time again in these sessions, but you need to understand that, because if you don't have the right superheat, you can start getting liquid back or wet gas, and then that's going to wash away the oil, cause lubrication issues. I did a one with Giacomo Pisano from Dorin, where he shows a video where they're constantly flooding back and watching the pressure drop on it as it's taking liquid into the compressor. Not smashing it right away, but it's taking that liquid in, and they know it's causing wear. But this is a sign for a technician out in the field ever go to check the graphs, that make sure that you have this superheat. Now on the design side, now you need to make sure that you can design to have that superheat. If not, then I think you'll have to have additional heat. Is that correct, Nabil?
That's absolutely right. There are two forms of superheat. There's useful superheat, which is generated in your evaporator coils, whether that be refrigerated display cases or cold room evaporators or whatever that cooling load may actually constitute. And then there's non-useful superheat, which is picked up from the surrounding environment into the suction line and suction componentry. And those things, it really helps to have a kind of conservative, as in worst case, but also accurate figures for, because it does affect the resultant selection, and it does affect the perceived efficiency of that selection as well.
Yeah, awesome.
So
okay.
shall we?
Yeah, I think we should dive in. Let's get into some selection and what the things that we need to look for, what compressor options we could have, because I know when you're designing, and I went through lots of design courses and stuff on compressor selection, but one of the things that I want to talk about while we get this up after you start sharing your screen is that, like, the advantages of having more compressors and less compressors, because for sure capacity control is going to be way better if you have more compressors. You can, you know what I mean, stabilize them out, I think, than just having one or two compressors.
Absolutely. Can everyone see my screen?
Yep.
You got that, Trevor?
Yeah, I can see your screen perfectly.
Brilliant. Okay, so I've opened the latest version of the Bitzer software. So the first thing I'm going to do is I'm going to go to the CO2 systems window here, which is the middle left-hand side. We click on that, and we get this screen here. We can see our inputs on the left-hand side. We can see a pH chart here, and we can see a little system process flow diagram in between, in the middle. Our numerical outputs will appear on this bottom right-hand side that's currently blank. So the first thing to do is to look at your system type. So we've got flash gas systems here, and we've got Gustav Lorentzen. Now we're going to steer clear of the Gustav Lorentzen today, and we're going to stick with flash gas, because this is the most commonly found and explored transcritical technology that we are working with at the minute. So what we're going to do, we're going to leave the selector in cooling capacity mode, and we're going to start to enter the conditions that we want. And I'm going to start a bit simple stupid by not changing things that normally I would change. And I'm doing that deliberately so that we can see how we can affect our output in terms of selection. So we've got our LT stage in this first column here, and our MT or medium temperature stage in this middle column. We then have two more stages that aren't selected, and we'll talk about those in a bit. So we know that we want 100 kilowatts of medium temperature capacity. So we type 100 kilowatts in, and we know that we want 25 kilowatts of LT capacity. So we type that in here. We'll leave the number of compressors and the capacity ratios of those compressors as are for the minute. So now we come down to the SST. So our SST on our medium temperature is -7. And our SST on our low temperature is -29. So we have both of those figures in. Now, evaporator superheat of 5 is what most 5 Kelvin is what most
which is like 10,
commercial
almost 10 degrees
refrigerated
superheat.
display,
Yeah.
display case cabinets are set up for.
Yeah,
this figure is usually between 5 and 8, depending on what exactly the cabinet is or the load. So we will leave 5K because that's realistic.
Yeah.
For the
Like
suction line superheat, I'm going to reduce this. We usually find that suction line superheat for a relatively small system such as this, with limited interconnecting services length between the plant and between the evaporators, as in the cases or the cold rooms, we usually find it's between 2 and 3K, worst case. But we'll reduce that down to 3K for both. Or actually, we'll reduce it down to 3K for medium temperature. For low temperature, you are likely to generate a bit more non-useful superheat because you have a wider temperature difference between that suction vapor and the surrounding environment. So we'll put that in as 5K. Now we want to look at our gas cooler outlet temperature. Now this is dependent on our worst case outdoors temperature, external ambient temperature. So we're going to say that our worst case design external ambient temperature is 35 degrees. Now, for supercritical design, the temperature difference between that external temperature and the gas cooler outlet is usually 2 to 3K. Which would you rather use, Trevor? Shall we use 2 or 3K?
3K is fine.
3K, excellent. So that means that if we're working at 35 ambient, our gas cooler outlet is 38. Now, our intermediate pressure is usually between 35 and 40 bar. A very commonly used figure is actually 38 bar, which is, funnily enough, the same figure that we use for gas cooler outlet. So that's equivalent to a saturated CO2 temperature of 3.3 degrees. For the minute, I'm going to untip this internal heat exchanger, which is an added complexity. So we'll get rid of that for the minute. So I'm going to press play. Just to recap, we've entered our desired cooling capacities, 25 kilowatt LT, 100 kilowatt MT, and our desired SSTs and superheats, minus 29 for LT and minus 7 for MT. So I'll press play. So we've managed to deliver an evaporator capacity that's spot on, 25 kilowatts as requested. Our MT capacity is just under the 100 kilowatts that we requested at 99.7. Now, there are no variable frequency drives or inverters on this selection. So I think the key here is to realize that these compressors are just solid blocks that can only come off in the capacity ratio shown because there's no inverter. So I'd be tempted to then think, well, what happens when I'm at a different condition? So if we say that our temperature drops outside, so we have a gas cooler outlet temperature of 32, and we press play with those same compressors, our LT capacity hasn't changed because it's not connected to the ambient temperature, it's connected to the MT suction. However, our MT capacity has now increased from 99.7 to 120.1. But we don't want that additional 20.4 kilowatts. Who said we wanted it? Well, what happens if we remove one of the compressors? Oh, wow. We've now shot far under our desired 100 kilowatt. We're at 66.7. And this is why we want to add an inverter, because we don't want the system to be cycling between 66.7 kilowatt and the 120.1 kilowatt, just on the desire to somehow hit some sort of waveform mean of 100 kilowatt in between. So what do? We add an inverter. So frequency inverter, and well, actually it was already selected, but I hadn't varied the speed, so that doesn't completely mess up my example. But if I now increase it, I can see that my evaporator capacity at the maximum frequency on my MT inverter of 70 hertz is now about 77 kilowatts. Well, we haven't got back to our 100, so I'll go the other way around. I'll add the third compressor back, and I'll actually reduce the inverter speed. Well, we're at 40 hertz, we're 105.3 kilowatts, so we need to reduce it a bit further. We're now at 102.9 at 37 hertz on the lead compressor, and we're now at 100.5, so we're near enough there. We take off 1 more hertz, we're at 99.7 like the original selection. So that shows you the power of having an inverter, is that you can closely load match.
Makes a big difference. It definitely makes a big difference. And then it keeps that suction nice and constant, keeps your whole system running a lot better than that one compressor turning on, drops all the way down to 66, and then the other one bangs back on. And I've seen that many times in HFC systems, but I think it's almost a norm now to put some sort of capacity control on a rack.
Absolutely.
It should be standard if it's not.
Yeah, if we're to seek some sort of COP, as we state as an average, it's absolutely necessary to have it, because without that, what you suffer is a degradation coefficient from that cycling between two compressors involving start currents, transients, and all those effects which actually reduce COP. So if you actually want to hit that average COP, you need an inverter, you need a VFD. So awesome. Moving on, let's have a look at numbers of compressors. So is this realistic? Well, 3 compressors for 100 kilowatts is relatively realistic. I'd probably, for 25 kilowatts, 3 compressors is, again, sounds quite realistic, but your end user might say it's a bit pricey with that many bodies, it takes up too much space, so we'll go for 2. So what you would then do, you go back to cooling capacity, and you'd start again with 2 compressors instead of 3 on your LT, and press play. Oh, without forgetting to increase your gas cooler outlet back to what it was before at 38. So that's this is what you typically see I feel for 100 kilowatts plus 25 in a booster configuration, something like this.
So it's pretty close, you know, it's on like 24.9 kilowatts, you know, close to that 85,000 BTU mark. 2 compressors.
Let's see how close we can match without inverters. So if we switch the inverters off and press play, we're now at 22 instead of 25. So we need to go up a size. So let's make this bigger. I've made the first compressor bigger. Now at 23.7, that's not enough. So 26.5, we're a bit over now. So this is it. Basically, when you don't have an inverter, you are not using as much of a compressor, of a lead compressor, as you could do. So there are real benefits to having inverters for that reason as well. Although you do have to factor into account the cost of the inverter as well.
Yeah.
So if we then increase this size, 97.8, and we're now significantly over 100 kilowatts, we're at 106.7. Well, let's see what our capacity control looks like without the inverter. So again, I reduce my gas cooler outlet down to 32. And I now have the same LT capacity, because again, that's not connected to the ambient, but I have 129 kilowatts of medium temperature capacity. And now I don't have an inverter, so we go down to 2 compressors. and we'll basically be cycling between 129 and 75.5 kilowatts, just to show that example. And you know, the further you reduce your gas cooler output, as in the lower the ambient condition, the more compressor capacity each body will have. So you basically continue to face this issue of finding it hard to load match when you don't find an inverter.
Yeah, I don't think I've seen a CO2 system myself right now without some sort of capacity control on it. Any CO2 system, like mostly inverters, some digital or suction capacity control, but I think pretty much most of them will have some. They will all have, that I've seen, some sort of capacity control, mostly drives on it. And lots of people think the drives are difficult, but they're not. If you went in and understood what the compressor needs, you input the compressor information into the drive, because you don't, the people, oh, there's 1,000 parameters. Yes, there is 1,000 parameters, but you don't need to change 1,000 parameters. You just need to change the specific parameters for that specific compressor.
Absolutely. There are options here. So one of the first things to note is that on the LT stage, we've used the standard series of compressor. If you go into technical data here and you have a look at the LT machine, you can see that its maximum pressure is 30 bar on its suction and 53 bar on its head, on its discharge. Now, for most of the systems that I specify in the UK, this isn't enough. This isn't high enough. They, apart from the discharge side of the system, which is 120 bar, the rest of the system is to be 60 bar for most specifications. And therefore, what I would have to do is not use this standard range of Bitzer LT, but use the ME or high standstill pressure range. So I would select that, and I would see that my maximum pressure is now 100 bar on both the suction and the discharge side of that LT booster compressor. And now I'm happy. So that's one thing to know. So then we go cooling capacity, put this back to 38, the gas cooler outlet, put this back to 3 compressors on the HT, put my inverters back because I want them.
Yeah.
And again, what I'm trying to do is make the selection more realistic as to what we would actually see delivered in the field. This is really important. Again, very, very close matching with those inverters. We have options on our MT side as well. So we have a design system compressor only COP here. So by system, I mean comprising both the LT and the MT. I don't mean inclusion of fans or controllers or crankcase heaters. I just mean the amalgamation of both LT plus HT, but compressors only of 1.51. If I now look at a different MT option in Bitzer, this is Ecoline, and we'll go cooling capacity again, and we'll go through the exact same process. So 2 on our LT, 3 on our MT, and 38 gas cooler outlet. Nothing else has changed. And press play. We've now got, again, very close matching at design conditions, but our amalgamated LT plus MT COP is increased from 1.51 to 1.66 because we're using these Ecoline higher efficiency compressors. Now, what's different about these? Well, they use the LSPM motors, or line start permanent magnet motors, and this actually improves their power handling and therefore their efficiency significantly, and that's reflected in these results. The power draw for those MT machines is now lower than it was for the standard range of Bitzer MT compressors. Will there be a capital cost impact to that? Yeah, probably, but what are you trying to achieve with your system?
Yeah, exactly. So this is good information. What's what's the penalty or not when you go from a 50 hertz design now to a 60 hertz design? Because we know that when we're running at 50 hertz with these compressors, I think it's 1450 RPMs. When we're running at 60 hertz, we're running at 1750 RPMs. We have some more mass flow. We got different capacity. What's your thoughts on when you're sizing a 50 hertz system versus a 60 hertz system?
In terms of maximum inverter frequency?
Well, just in the sizing of the compressors themselves.
Well, I would prefer to size at 60 because then you get a wider control range for that lead compressor. And therefore you will have less kind of gaps in your basically in your output when you're staging. So for me, I would prefer to see it at 60, not 50.
Mm-hmm. Awesome. Okay, so this is basically, and then the different compressors that we got up there. There's, we got a 2HME 4K and two of them for or 2FME 4K for that's the low temp, and then we got a 4HTEU 20LK and then a 4TEU 25LK and then a 4TDU, two of them. 4TDU 25LK, but you can play around with these just like Nabil shown. You can change them from a bigger capacity, a lower capacity, move that frequency up and down to change it to see where it's getting a better capacity control. Because what you want to do, you do not want to be have compressors banging off, short cycling. You want it really smooth in that transition. So as that VFD starts to ramp down, that last compressor turns off, then that VFD will ramp back up. And this is all in the control side, but the first step is selecting the right compressor to hit every gap.
Absolutely. That's absolutely critical. So one way to look at this is to up that lead compressor in size, press play, and then we've actually exceeded the current consumption on that at 65 hertz. Bring it down a bit. We're now at 59 hertz and we're still over capacity, so we're 104.2 kilowatts. So we come down to 57, 55, now it's 101 kilowatts, and we come down too much, 53 hertz, 99.5. Our COP is reduced at design conditions by 0.01. And then we can look at making this lead compressor the same size, displacement, or internal volume as the fixed speed compressor. So if we go D to U25, that's the one, that's going to come down to get 100 kilowatts now. So at 47 hertz, we're still 10 kilowatts over. And then if you come all the way down, you can get to 100 kilowatts. But that's an enormous waste of a lead compressor at design conditions.
Yeah.
In real life, that thing will hardly ever run. So for me, and the design COP has come down even more.
Yep.
So what Bitzer's automatic selection suggested, for me, was the best of those three options. Yeah, awesome. And it's about looking at that at a full range of conditions, as Trevor says, knowing what sort of part loads you're likely to experience, knowing what ambient range you're likely to experience, and actually how many hours do you spend at 10 degrees, 15 degrees, 20 degrees each year? Because if you're looking for peak efficiency, it makes sense to base that on the ambient bracket that has the highest number of hours per year. So here in the UK, it's something like 10 or 12 degrees Celsius. That might vary where other people live. So there's lots of things to consider when you're going about making these selections.
Let's dive in a little bit into the parallel compression. I think this is something that needs to be used more. I don't see it enough here yet in North America, but parallel compression is something that is going to be widely used, and it's a high ambient strategy to really digest the flash gas. You don't have to put all that that flash gas coming from the fluid from the gas cooler when you're in transcritical through the high pressure valve, instead of going through the flash gas bypass valve into the medium temp suction, now you're going into a different suction at a higher pressure, reduced compression ratio, and increasing the efficiency of the system when designed properly. This can lead to smaller compressors as well. What are your thoughts on parallel compression, Nabil?
I think parallel compression is an incredibly useful tool in higher ambient regions. So, for instance, Southern Europe, southern states of the USA, for instance, it really comes into its own. But that's not the only time. It actually has a strong business case for systems that rely on heating, where heating is expected from the discharge side of the systems. It's not just seen as an afterthought or a would be nice. It's actually demanded from the system, as if the system is also simultaneously a heat pump. Because when you are artificially elevating discharge pressures, or you're running a false load, or you're using a gas cooler bypass to make sure that you maximize your heat recovery, what are you going to have? More flash gas. And that keeps your parallel compressor running for much more of the year than what it would do if it was only being used in high external ambient temperature conditions for a few hours each summer per year.
Yeah.
So
yeah, I totally agree with that. And we'll see a lot more of it coming out. I'm seeing more manufacturers starting to use it, test it, and I think it's going to be a good option.
Absolutely. Let's have a look what happens when you click the parallel compressor button. So no, your first question is basically the same as the first question for the design of the other two suction groups. How many compressors are you willing to chuck at this?
Exactly.
I dare say the majority of systems of this size will not accept having more than one parallel compressor. They won't. They won't.
Yeah.
So we go cooling capacity again. Check that all our figures and selections are still appropriate. You'll see that for this one, an inverter is mandatory. Well, that's absolutely right. The amount of flash gas is so sensitive to the system conditions that there's no way that you could run a parallel compressor fixed speed.
Yeah, exactly.
A lot of people say, well, what happens when you take your parallel compressor down to its minimum speed? Can you then run it in an on-off manner? The answer is no, can't. So when you get to that minimum speed, your only option is to revert back to using your flash gas valve, or your receiver pressure regulator valve, as some people call it. So we've got cooling capacity, so it's going to do the selection for us again. We've got parallel compressor ticked. We've got suction line superheat, 5 degrees. Now, that's not really that realistic, I find, for parallel compressor suction. It's either closer to 0, or if you put some sort of heat exchanger on it, it becomes a lot more than 5. So take your pick. I'd say the most safe thing to do is to actually put a plate heat exchanger on it and exchange the heat with the gas cooler outlet line, in which case this will become, we might actually have an option for that here. So I'll put the suction line superheat as 0, and I'll add a flash gas to gas cooler outlet heat exchanger here to protect it so that it has some level of superheat. And that's going to be something, anything from 20k to 30k. We'll put 20k. So press play. And wow, look what's happened to our design COP.
Huge.
It's gone up 1.66
from 1.51, I think it was. Well, it was 1.51 first, then we went up to 1.66, and now we're up to 1.86.
And that's an incredible result. Now, as we discussed, we don't spend much time per year operating this. So we have to start thinking, well, what does it do lower down? One thing I'm interested in is this parallel stage. What frequency is that machine now running at? 57 hertz. Well, I'm going to play chicken with this. I'm going to see if I can change that, the size below. No, it's not happy with me for doing so, which is really sad because I was trying to actually widen the frequency range of that compressor to the point that it could actually run with less flash gas, less displacement, but I haven't been able to do it. So my option is the full GTE 30K with a frequency of 57 hertz at design conditions. Let's test the next ambient bracket down. So let's say let's put the 32 degrees gas cooler outlet in again and see what happens. Is our parallel compressor still running? Yeah, it's still helping, 48 hertz. Let's go a fair bit lower. Let's go to 27. IHX superheat too high, maximum 19.64. The good news there is that that's likely to come down because there would be less heat in the gas cooler outlet anyway. So that's what's limiting that. So if I change the 20 to 19 and press play again, our parallel compressor is now at 32 hertz. We're approaching its minimum speed now. So we know that it's going to cut off in a minute. 26, again, adjust your superheat on your internal heat exchanger. We're at 30 hertz.
I think that's where
So we
max
go
is
to
out.
25 degrees. Again, adjust this appropriately. We're now at 28 hertz. Now I know that the minimum frequency is 25. I think it is anyway. So let's see what gas cooler outlet that's equivalent to. We'll try 23. And we'll put 15. Too large, too many compressors. Choose smaller or less compressors. Basically, we're asking our parallel compressor to run at a frequency beneath its minimum, so it can't run. And we're then back into flash gas bypass mode.
Yep. That's super cool because you got to go through each one of these steps when you're sizing, doing those sizing, and you got to check each time these different scenarios that potentially could happen. It's very important to do that.
Well, this is really what tells you not what the peak effect of your parallel compression is, but what your annual average effect of your parallel compression is. And that's what matters to the bill payer. That's what matters with your business case in terms of return on investment. So we may have seen 1.51 to 1.86 in COP, but what really matters is the net impact. And the only way to do that would be to do what we call a TUI calculation, or a total equivalent warming impact calculation, where we take a range of external ambient temperature brackets, a part load profile for that, and what our gas cooler outlet or condensing temperature is at each one of those brackets. Each one of those temperature brackets has a number of hours allocated to it per annum, and each one of those brackets will have a different COP, and that COP will depend on whether this parallel compressor is running or whether it's not running and it's gone back into flash gas bypass mode. And using a tool such as TUI, you can then calculate what net annual average effect that parallel compression has on the efficiency of your system.
Yeah, and this is what Omega Solutions specialize in. So if you guys are looking for people to help you with these calculations, help you with this design, definitely reach out to Nabil, reach out to Omega Solutions. So, okay, we just kind of took a look at Bitzer using their calculator. Why don't we dive into Dorin now and take a quick look at their software if you want to select their compressors.
Absolutely. So this is Dorin's software. This is how it comes up when you open it. Again, you can look at individual compressors, but when you're dealing with a booster system with an intermediate vessel and flash gas return or parallel compression, you can't use a single compressor window. You have to use something that takes those mass flow proportions into account. So what you do is you go to refrigerating systems, and guess what? You pick CO2 booster. You can have LT only if you want to do an LT only system, or you can have MT only. And you can have a system that I haven't seen in the field now for 12 years, which is a CO2 cascade. We're not going to look at that. We're going to look at our CO2 booster. So calculation. And again, it's a very, very similar procedure. So we have got a number of things. We've got an info window, bottom center. We've got a process system diagram on the right-hand side. We've got our numerical outlet center top, and we've got our inputs on the left-hand side. So configuration. Again, we've got a number of things we can pick. The most common and standard is the flash gas bypass system. Parallel compression is included again. We've got various type of ejector systems, which isn't within the scope of this discussion, but again, you want to take the efficiency hunt even further, this is what you would end up looking at. So let's have a look at standard flash gas bypass. So required capacity, MT, which we can see here, 100 kilowatts again. SST or evaporating temperature -7 Celsius. Evaporator outlet superheat 5 degrees. Suction line outlet superheat. Well, this isn't 2 or 3 degrees, because what this actually is the evaporator outlet superheat plus that suction line superheat or non-useful superheat. So this would actually be 8 degrees on this method of selection, on Dorin's way of doing it. So our gas cooler outlet temperature, based on an ambient of 35, is 38 degrees C.
So Nabil, just a second. So that evaporator outlet superheat, would it be plus the 8K? So 5 plus 8, that's actually what the compressor is going to see, 13K coming back?
No.
No, it's 8. Okay.
5 from the evaporator plus 3 from the suction line gives a total of 8.
Okay, a total of 8
into the compressor. Now you'll note we're being asked to input a figure that we didn't have to input into Bitzer, and that's the gas cooler pressure. Now, as some of us may know, in supercritical mode, there is no pressure to temperature relationship. So for a gas cooler outlet temperature of 38, how do we know what our discharge pressure is going to be? Well, we have algorithms in our PAP controller, in our system controller, that tell us what either the capacity optimal or the COP optimal, or some in between of the two, what that optimal discharge pressure is. Now, Dorin's not doing that for me. So what am I going to do? Well, guess what? I'm going to steal the value that Bitzer calculated to be the optimal. So I put my gas cooler outlet back to 38, press play in Bitzer, and the optimal high pressure is 93.7. Now, don't feel it has to be from Bitzer what the optimal gas cooler pressure for the gas cooler outlet temperature is. In fact, Danfoss for 38 degrees use a slightly different figure. Bock for 38 degrees use a slightly different figure again.
Yeah.
Each manufacturer has its slightly different interpretation of what the optimum gas cooler pressure is for a gas cooler outlet temperature in the supercritical range of operation. But I've just used the Bitzer figure just for simplicity right now. So our receiver pressure, or our intermediate pressure, is 38 bar, as we used on the Bitzer selection. And now we have a look at LT. So we've got a required LT capacity of 25 kilowatts and an evaporating temperature of -29, an evaporator outlet superheater 5K, and add the non-useful superheat on to get a suction line outlet superheat of 10K into the compressor. So we've input what we need and we press play, press calculate, and you will see that we've got really poor performance. We're 100% down on our MT and we're 84.8 down on our LT. And this is because I forgot to change mode from calculation to selection. So what this has been doing is trying to force my numbers through just one CD150M and one CDS 101B, 4 compressors. So we go into selection mode and we press, we make sure we've got everything selected. We're going to go for 3 MT machines with 1 inverter. And we're going to go for 2 LT machines with 1 inverter. And I'm going to see if I can press play. It's not happy for some reason, so it's something I haven't done quite right.
Filter compressor models.
Press play. Now it is still not actually selecting, so I'm going to put the models in myself, I think, on this, because we're not getting what we want, which is a bit disappointing. So I'm not really sure. Trevor, do you have any idea
what is the filter compressor models? That button above the calculate.
Yeah, filter compressor models.
Does not accept floating point on non-value. So
I'm going to close it and I'm going to open it again because it may have crashed. So if we make sure this time that we go into the right mode first, so selection, we might have better luck this time.
Yeah.
So 100, -7, evaporator 5, suction line 8, gas cooler outlet temperature 38, gas cooler pressure 93.7, and receiver pressure 38. I'd like 3 on there with 1 inverter. LT, we want 25 kilowatts at -29 with an evaporator outlet superheater 5 and suction line outlet superheater 10. I want 2 machines, 1 of them with an inverter.
oh, it's still not calculating for some reason.
Calculate.
There you go.
And we got it right.
Model. Yeah, you nailed it.
And that's what we get. Now, we've got a reserve capacity of 76.1 on the MT and a reserve capacity of 8.1% on the LT. Let's have a look. We've got a net COP of 1.68. So we can play exactly the same tunes that we did on Bitzer. We could go to parallel compressor and add a parallel compressor. We could take inverters off. We could change the range of compressors that we're using, etc., etc. From there on in, it's not really a great deal different. Is that fair to say, Trevor?
Yeah.
Excellent. Any questions on that?
No, I think that's so important to do because you want to go through the different different manufacturers to get a better understanding of what it looks like, and see what's going on, because this has a reserve capacity of 76.1. So that means that's way bigger than what you would need. So then you would go back and try to drop that off, correct?
Absolutely. And I'm not so sure why it has selected something that is so oversized. So I'm going to play games with it. I'm going to play chicken. Now I'm only 45.8% over. Now go to the smallest one in that pro range. Actually slightly more over. So then I'm going to try and manipulate it in terms of model, but it's I'm not sure why it locks us into certain things that are a bit oversized. So I think what you have to do if you find the selection to be not particularly clever or useful is you have to go in and manually manipulate it until it gets you exactly what you want. And we're nearly there. So we're at minus 13. So we're slightly under now with the current selection that I have. So this is what you have to do. Now we're 5.8% over on MT and 8.1% over on LT. So we're less wasteful of compressor displacement right now than what we were.
Exactly. And that's what you got to do. You got to try to fine tune that selection and to get it right, because now on top of that, you're going to have the drive. You want to make sure that drive is going to go from that 38C down to 30, down to 25, because as the winter comes or the colder season, you want to make sure that you are designed for all different conditions, which is really cool to see. And you want to compare. Where like what is going to work best for you. And the big thing is that it's like, for me, working with all the different compressor manufacturers, like, how do you get access to them? Is there access to that compressor manufacturer where you're located? Can you get parts for it? Can you build a good relationship with them? The people know where it's at. And these ones that we're talking about, they're global, so it's not very difficult. And you need to dive into this to learn even a bit more. Okay. It's just like we're just showing you how to do this very quickly, but it's very important to dive into all the behind the scenes. Why don't we dive into one last one? Because we're starting to get up on time here. Because I see a lot of racks now come out. You got Bitzer on the medium temp side, and you got Copeland Scrolls on the low temp side. Can we take a quick look on sizing a few Copeland Scrolls for the low temp booster side? Because I'm seeing more and more of that.
Absolutely. So this is what you will be familiar with if you open the Copeland Select 8 software. This is the desktop version. So what you would do, you would go Tools, and you would slide along to here, R744 Systems Calculator, and you would press Booster Cycle. And that brings up this window here. So we're talking about scrolls on the LT, and semi-hermetic reciprocated compressors on the MT. So scrolls on LT, recips on MT. So let's input our same scenario that we've been working with. So 25 kilowatts of LT with an evap temp or SST of minus 29 Celsius, evaporator superheat 5, suction line superheat 5. And HX subcooling 0, MT evaporating will be whatever your MT is going to be here. And you can see that this MT evaporating temp T8 here is linked to this input cell on the low temp side. So that's going to be minus 7 Celsius. Receiver absolute pressure bar 38, as we used for the other ones. Desuperheating 0. We're not doing any desuperheating at the minute. So now we look at our medium temperature parameters. MT required evaporator capacity 100. That's linked to that cell. MT evaporator superheat 5. Suction line superheat 3. Now gas cooler pressure, we're going to use the Bitzer optimized figure of 93.7. for a gas cooler outlet temperature, which Copeland call cool gas liquid temperature, same thing as gas cooler outlet temperature, 38. Heat recovery, I'm not specifying any heat recovery at the minute. So what we now
need to update that cool gas liquid temperature. I think they need to update that to gas cooler outlet temperature.
I would dare say, and Copeland, I do apologize in advance, this isn't an industry standard phrase as far as I have seen, but I might be wrong. So what we want to do now is pick some compressors for this, because you'll see there are no output figures come up, which isn't good. We want to see outputs. So what we need to do is select fixed speeds and leads. So we want a lead compressor, and we also want a lead compressor. I've just selected any compressor for the minute, the first one in the list. So what you can see here is that we've got far too many compressors. I only want one fixed speed and one variable speed compressor on my LT, which I've now got.
So this software doesn't do the automatic selection, or can it? I don't remember.
No, this one can't, I'm afraid. So what you've got to do is toggle between these values until you get what you want. So if I change that to the larger lead, it then turns out I can have a really tiny fixed. And what's the point in that? Basically, you've oversized your lead, and then you've got a tiny fixed speed. So I'd go with the smaller variable speed or variable output lead, and then pick a similar size displacement wise to it for the fixed speed. So we've got one ZOD34 variable and one ZO46 fixed. That's what I would do for the LT. Now we move on to the MT. Well, again, do I really want 14 4MTL05 compressors? No, I really don't. Okay.
14,
that would be a world of pain. So I'll go for 2 4MTL50s for the minute. But then we've got a bit of a capacity imbalance here between our leads, because I haven't upped that either. So again, you want them to be roughly the same size, the lead and the fixed. So let's play chicken with this then. So let's say we'll go for one that's around 30 on the inverter. Okay, didn't really like that. So that's 25. Yeah, that's still not ideal. So what I'm going to do now is move down the range on here. So 2. Now we're at 46 there, but we, as far as I can see, are still far too different in terms of the displacement of the machine, as you can see from the max capacity. So what I'm going to do now is investigate what happens when I go for, that's it, we're getting there. So now we've got 44 coming off the lead and 45 each. Is that right? Yeah, something like that. That's a good selection.
But we are still 32,000 kilowatts above, so it's still quite a bit bigger than what is needed.
Oh yeah, actually, sorry, yeah, you're right.
No,
yeah. Okay, so let's come down.
Well, that's the thing, is you got to play around with the software, because if you incorrectly select the sizing, this will impact the whole design of the system and how it runs. But
Absolutely.
you got to go through it.
Trevor, you're looking at pack capacity, which includes the LTTHR. You
Okay.
need to look at delivered evaporator capacity, which is where you split the connected load on the MT out from the total cooling load, including the LTTHR.
So that was my bad.
No. It took me a while to realize what was going on as well. So my bad too.
No, but this is it. You got to walk through it and see. So that was a total pack. So that delivered at 100 kilowatts. I think that one doesn't see, it's not changing at all, right? The delivered one, even every time you change it, it doesn't change that one. I think that's what you're looking for, 100.
Yeah,
so that the whole
absolutely.
pack is 32. So the medium temp,
if you look at the THR of the LT, it will be its evaporator capacity plus the power input. So that would become 30. Plus any non-useful superheat, which will increase it up to the 32.48 that you see here. Plus, obviously, the non-useful superheat on the mass flow of this.
So they're adding it all together.
So when you add it all together, your total cooling capacity of those compressors, which is different from connected load capacity, is 132.48.
There's so much knowledge here. I'm always learning. Like, this is awesome. I love it. I love sitting in and learning this. But this is kind of what I'm seeing.
You're learning, but I'm remembering as I go along what I've learned in the past. So it's a bit of catching up as we go. Yeah,
no, I love this. Nabil, this has been great. Like, and we only spent, an hour or 55, 56 minutes, maybe 60 minutes. And I learned so much. Like, hopefully out there, you guys have been listening to this and the key things. And I know Nabil's talking about kilowatts, and if you're on BTUs, that shouldn't matter. And he talks about Celsius and, we're in North America, you're in Fahrenheit. None of that should matter. You should understand the process of what you need to do in refrigeration. And that's how you're going to get better. Just like when you're sizing these compressors, sizing and selecting compressors, I highly recommend you go out and get into these softwares. They're free. These manufacturers are doing a great job providing all this software for free for you to go and check them out and take a look at them, get into their documents, get into their technical papers and look at them and how they run. Can they use a drive on them? What's the range? And just playing around with this, I seen a few things, even when you were on the Bitzer software, just moving it up and down, seeing that frequency change depending on the compressor will make a big deal in those selections.
Agreed. In my opinion, the Bitzer one is the one that's most intuitive, especially if you want to do calculations because of that variable inverter frequency option.
Yeah, no, exactly. Nabil, thank you so much for taking the time to do this. How can people find out more about you? I already said it. Nabil from Omega. These guys, this is what they do day in, day out: sizing, selection, design on CO2 systems. Reach out to them. But how can people find out more about you, Nabil, or find out about Omega Solutions?
Please take a look at our website. It's www.omega-solutions.co.uk. Please feel free to send me an email at nabil@omega-solutions.co.uk. And I look forward to meeting you and to assisting you in whatever way that we can. Thank you very much.
Nabil, thank you so much. And once again, dive into this, learn a little bit more. And every day, if you learn one thing, at the end of the year, that's a lot of more knowledge you're going to have than the previous year. Each time I do these sessions on CO2, I'm learning something. Hopefully you're learning something each time you listen to this. I want to thank you for taking the time to listen to this. And I'll see you at the next CO2 Monday in Refrigeration Mentor podcast. See you later, everyone.
Thank you, everyone. Bye-bye.